So instantaneous slope is like instantaneous speed, but it doesn't have to be speed of movement. It could be rate of change of anything. For example, think of x squared as the amount of money in your bank account. You started out with a bunch of money, and apparently you were spending and losing all your savings. Eventually you ran out completely, and then you started saving again. Okay, that's what this would mean if that was your bank account. Now, what the derivative is then is the rate of savings at any point in time. You were spending, so the rate of savings was negative. And at this particular point of time, the rate of savings is exactly this instantaneous slope. As another example, let's take the function x cubed. The formula says the derivative of x cubed is going to be 3 times x squared. Let's graph x cubed. X cubed looks something like this. Now, what does 3x squared look like? Well, it looks like x squared, except times 3. We drew that a minute ago. Okay, so how are these related? The formula says this should be the derivative of this, which means that the slope at any moment here is given by the value of this equation down here. Now, does that make sense? Well, notice that this is always positive. That means this will always be increasing. Okay? And notice that it's 0 right here at that one moment in time where this is temporarily flat. Okay, so it's at least plausible by looking at it that this could be the derivative of this. And the formula says indeed it is. So a study of the derivative involves 3 parts. The first is by far the most important. That is to really wrap your mind around this concept of the derivative, what it means to have an equation giving you the instantaneous slope of your original function. And also knowing how to apply that. There are so many applications. This was invented by Newton for physics to deal with forces. It's been used in so many areas, including optimization, probability. I wish I had time to explain all of the applications. And that's, of course, the most important part of calculus is knowing how to actually use this to do those cool things like optimization. The next part is learning how do you do the mechanisms of taking derivatives. How do you take your x cubed to 3x squared? And we saw that that was just plugging in this formula. All right? But what if it wasn't? What if your function wasn't of this form? Well, you have some rules for trigonometric functions, for fractions. You have rules that say what you do if 2 functions are multiplied together. For example, here is a list of rules for derivatives. This is from the University of Arizona. And this list is everything you need to compute derivatives. In fact, this list is way too much. The whole second half of this list can be derived from the first half. So really, all you need are these rules and this one here, and you can compute derivatives of virtually anything you want. The mechanics of calculus are so easy. It'll be some of the easiest math you've ever done. That's the beauty of calculus. Doing these, calculating derivatives, is trivial. The third part of the study of the derivative is moving the curtain and seeing how did we do this magic trick. We have a trick that gives us these formulas. For example, I pulled this formula out of a hat. And those who are curious about mathematics will want to know, how did I get that formula? And so usually the study of calculus will also involve doing some proofs and derivations of these formulas. And I'm going to spend the last few minutes doing the derivation of this particular formula, because it's kind of fun. So notice that I want to show that the derivative of x squared equals 2x. All right. Now notice, if I have x squared here, again, let's draw it. To calculate the slope at any point, let's call this point A, if I want the instantaneous rate of change, what should I do? Well, one thing I can do is I can take another point that's not very far to the side of it. Let's call that A plus h. And if h is very small, then these are almost the same point. What if I calculate the slope of the line that goes through those 2 points? All right. Now, calculating that slope should be pretty easy, because the value of that's just a plus h squared, and the lower point is just a squared. All right, we're just plugging in values there. So what is the slope? So slope equals the rise, which is a plus h squared, minus a squared. That's how much it went up, over the run, and the run is just h. Okay? Now, the derivative is simply, now the instantaneous slope would be the slope if h was arbitrarily small. You can see that if we make h really small, those points are very close together, and you're basically going to get the tangent line. Okay, so we want to know what is the slope as h is very small. So you have this notion of a limit. H goes to 0 of this formula here. All right, that means let h be arbitrarily small and see what value we get. Now the cool thing is we can simplify this. All right. Because a plus h squared just becomes a squared plus 2ah plus h squared, and then we subtract the a squared there. And notice that these cancel. So what is this? This is just 2ah plus h squared over h, which equals 2a plus h. All right. So the slope equals 2a plus h. Now we had to take h not 0, or this fraction wouldn't have made sense. But that's where this comes in handy. We want to let h be arbitrarily small. So the limit as h goes to 0, since these are equal, then that's going to be the limit as h goes to 0 of 2a plus h. And now it's obvious what that is. If h is arbitrarily small, then this just equals 2a. Voila. That's exactly what we were trying to prove. This says for every a, for any value a, the slope is 2 times a. That's the same as this, except we're just plugging in x instead of a for a variable. So we've just proven the derivation of that rule, that the derivative of x squared is 2x.